All right, welcome back everyone after the second midterm. I can see some of you survived. We lost a few, but that could be just to the upcoming holidays. All right, so we are going to talk about the EM algorithm more, which I hinted at in last lecture. And it's actually going to be a way to fit a mixture model. So we did talk about mixture models last time as an alternative to doing clustering, for example. You could do k-means, or you could instead use a mixture model. We didn't talk about how you learn a mixture model from data, and that's what the EM algorithm is going to be for. At least that's one example of it. All right, so do things work? No? Forgot to put this. Okay, so yeah, let's do a quick reminder of what a mixture model is. So we have, say, m data points. And if we want to model it as a mixture, so the distribution P of x essentially can be written as the sum over the k mixture components of the mixture proportion, which is the probability of one of the components. So you take a draw, pick one of the components, and then depending on what component you got, now you draw a sample from a distribution that corresponds to that component. Okay, so this is just mixture model in general. Specifically, we talked about the Gaussian mixture model, where you can think of the distribution from each component, from the ith component, for example, as a Gaussian with certain mean mu I and covariance sigma I. It indeed has something to do with people walking. I can see as students are walking and it starts to vibrate more or less. But I hope it's stable enough for yeah, people in the back.
Obviously, what we need to do is have people like alternate feet to cancel out the vibrations.
Yep. Yeah. Okay. It's not, yeah. I mean, it's very annoying standing here, but I think, yeah, from further away, it's probably better. Yeah. Okay. So, yeah, so we talked about Gaussian mixture models, where again you have, say, k components. So you could be fitting, imagine you have some data where what these contours show is essentially you're fitting a Gaussian with a mean, which corresponds to the center, and a covariance matrix, which is represented by the ellipse, right? And we can have one center and one ellipse, or the covariance, for each component. So this would be Gaussian mixture model. So what are the parameters of a mixture model? They are the mixture proportions, Pi. So we'll refer to this, the probability of picking any one of the components as Pi. So that's one parameter, or a set of parameters, k parameters actually. There's going to be, at least in the Gaussian mixture model, there's a mean for each of them and a covariance matrix. And the reason I presented the general mixture model here is that we talked last time about what happens if not all your variables are continuous. So the continuous ones, maybe you can model as a Gaussian. If you have discrete or some other categorical one, you can use different, you just have to replace this P of x given y. So given the ith component, you can put in the corresponding, for that particular xi, you can put in whatever distribution you want. It doesn't have to be Gaussian, right? So you could put them as jointly Gaussian, or you could have P of one of the features as Gaussian, the other one as something else, right? So you can have whatever distribution you want, you can plug that in here. But specifically for Gaussian mixture models, so now we talked about this particular model, we didn't say how we can learn it from data, right? So that corresponds to learning all of these parameters given some draws from this distribution, right? So what does the draw look like? With probability Pi, you pick the ith component, and then you draw a point from that particular, the corresponding distribution. A Gaussian with mean mu I and covariance sigma I, right? And how do we estimate its parameters? Well, you'll say, why not just do maximum likelihood? We have been doing that so far. Whenever we have a parametric model, we use maximum likelihood to compute the parameter estimates, right? So it turns out that in this case, you can try to do that, but all of your estimates are actually going to be coupled for all the different components. And the reason really is that because we don't know the labels here. So one way you can think of this problem is as if you're trying to do classification using k classes, and each class will fit a Gaussian, right? In the standard, when you're trying to do classification using under such a Gaussian model, which was known as the Gaussian Bayes classifier, right? We talked about that. We knew the labels. So we could only use data from that component to estimate its mean and covariance. We know which component each data comes from, essentially, right? And here we don't know that. So we have a hidden variable, which are sort of these labels, if you think of this as a Gaussian Bayes modeling in classification, right? And we use EM to learn these parameters. So EM in general is a method to deal with hidden data. And we'll talk about it in the specific context of first learning the mixture parameters under this Gaussian mixture model formulation. And later we might talk about other possible ways you can use EM data. But it's a general algorithm that tries to, where in problems where you have hidden data, it has two steps. The first step, which we call the E steps, tries to fill in the hidden data. So for example, in this mixture modeling framework, it's going to try to estimate the labels. Okay? And the M step is now going to apply standard maximum likelihood estimates, or you can do map, to estimate the parameters of the model. Once you know which component each class likely came from, you can hope to do maximum likelihood inference, right? And we'll actually see some nice properties that even if you do it in this iterative step, so you're going to repeat these two steps many times, because you'll start with some random initialization of your parameters. Assuming that you know those parameters, the randomly initialized ones, we are going to fill in the hidden data and then estimate the parameters and keep cycling back and forth. We'll show that this whole procedure actually converges and it monotonically improves the likelihood ratio, okay, or the likelihood under the model. Not the likelihood ratio, but the likelihood under the model, right? So we'll show that it actually converges to a local optimum of the likelihood. All right? So it's not it won't get you to the maximum likelihood solution, but it will get you to a local optimum of it. So let's start with a simple framework where we say that we know some of the things. We're not trying to estimate all the parameters. So let's say we have, again, our M data points. There are K classes. And say we even know the prior probabilities of each class. And we know that each class has a common covariance, which is just sigma square I, right? A very simple setting. We don't know the means. So we are only trying to estimate the means of each of the components. Then essentially when we are doing maximum likelihood, here we will be maximizing the probability of the data, right, for those parameter settings. And we know that we can follow some steps. For example, we can write down the probability of our data, x1 through xn, as the product of the probability of each one of them, because all the data are independent, right? And each one of them, how is each data point drawn? It's drawn from this mixture, right? So this is just plugging in, instead of p of x, we are plugging in the sum over all the k components, probability of drawing that particular value xj under each component times the probability of that mixture component, right? So that's just, we are just marginalizing over the class because we don't know the class essentially, right? And we have already assumed that each p of x given each class is just Gaussian, right, with mean, corresponding mean mu I, and covariance we have assumed here to be the same, sigma square I. So the problem just reduces to doing this, right? Notice that if we did have the labels, we would be, instead of just maximizing the probability of our x's, we would also be maximizing the probability of the y's, and then we actually don't have to do this marginalization over the class, right? We exactly know each class, and we can just do maximum likelihood estimation for each one, which will be decoupled. But now, all the estimates are coupled because we have the sum over all the classes. All right, so what does EM look like here? So first I'll just show you what it is, and then we are going to derive it in more generality. But this is what the E step corresponds to. It's going to be, you simply compute the probability that a point belongs to a particular class. That's the expected class label, right? So we are going to, for each point, compute the probability. We don't know the y, but we are going to compute the probability that the y is I, conditioned on now that you've observed that data point and whatever is the current setting of your parameters, because you're going to initialize them randomly. And notice that that is easy to compute because you're just talking about probability y is I given xj and your set of parameters, right, mu's. And that is just by using Bayes' rule, you can write it as the joint probability under the mu's. Let me just say mu's here, right, divided by p of xj. Right? And we are essentially, we want to calculate this probability, right? And for each I, so finally they all have to sum to 1, right? The probability that the class was 1 or the class was 2 or the class was k, if we sum up all of these, they have to sum to 1, right? So we can actually pretty much ignore the denominator. All we have to work with, and in fact the numerator also, we can write it in the form that we know the values. So we know what p of xj given y looks like. We don't know what p of y given x looks like, right? So we are just using Bayes rule again. So this times that, and we still have the denominator, right? But we can essentially ignore the denominator and essentially just compute the numerator, which corresponds to this Gaussian probability times, so you're computing a Gaussian, we know the mu's, right? So you're just computing for each mu I, you are computing this value of the Gaussian, and you're multiplying it with the class probability, which are again parameters that you have assumed are known, right? And then you just normalize them. You want all, once you do it for all I, they have to sum to 1, right? So you can just simply normalize them. So this step simply corresponds to evaluating a Gaussian and then normalizing them, multiplying it, of course, by also the prior probability of each class if it's not equal. So this step is equivalent, if you think of k-means, as assigning the clusters, right? Because we are saying we are finding, we don't find the one class that each component comes from, but we are calculating the probability that it comes from each class. So you can think of that as equivalent to assigning the clusters. And the M step is now going to be that if we know the assignments, we just update the cluster centers, right? Here the mu's are the cluster centers, the means, and we are going to update those. And actually what we have is now, this is the maximum likelihood solution, which was just the average of all points that fall within that cluster. Now you don't know exactly if a point falls in a cluster, you know a probability, right? So you just weight each point by the probability that it came from that cluster, right? So probability y is I given xj, you just use that as a weight. So this would exactly reduce to the k-means cluster center update step if there was exactly one class I to which xj belonged, right? Then it would just be the mean of all the points that fall within that cluster. Now instead of that, we are just plugging in these weights. Or another way to think of it is, again, you can think of having like multiple copies of each xj as many times as the probability, right? So we've talked about thinking of weighted data sets earlier, and this is just a weight on the data set. Does that make sense? Okay, so that's how it differs from k-means, that you don't have one class you assign it to, you have a probability that it comes from each of the classes, and you're using that in your ML estimate. Everybody okay with this? All right, so as I said, it's equivalent to updating the cluster centers, and here's what the EM then basically looks like for, this is for spherical and same variance Gaussian mixture model, right? You just compute the expected class, which is equivalent to compute, you initialize your parameters, the mu's in this case, to some value, you compute what the normal is, you also know the mixture proportions, and you normalize them to get these expected classes, or the probability that each point comes from a class, and then you compute the maximum likelihood of the parameters and update your cluster centers. All right, and then you iterate between these two steps. Now you use these new mu's and compute this again. Right? How would you do it for the, I guess I mentioned this, that this step is just in k-means, instead of soft assignments, we would be doing hard assignments, right? And this is just MLE with weighted data. So how would we extend this to general mixture models, where here we are just talking about updating the means, right, of each Gaussian. If we had unknown covariances and unknown mixture proportions, we can also update those in exactly the same way. Those are just additional parameters. Okay? So the way we do this is as follows. So now our parameters are all the means, all the covariances, and the mixture proportions, right? And each step is exactly the same, except that, of course, the Gaussian now you will be using will have a covariance matrix, which is initially you just initialize it to some random value, and the mixture proportions are also going to be whatever you initialize it to be. But now you're going to update not only your mean, but also your covariance, which exactly you can see the update is also very similar. So the standard estimate for the MLE estimate for the covariance matrix is just you look at the empirical covariance, right? The 1 by n sum xj minus mu i's, right? Now we are also doing that in a weighted form. So we have a probability for each point belonging to a component. So we multiply by the probability, and we also divide by the sum of those. And similarly for, we also need to update our mixture proportions. So the mixture proportions are, again, you would count how many points belong to, if this was class priors, right, where you knew the labels, you would just say, of all my points, how many are of this class? Now, we don't know how many are of a class, but we know what's the probability that of a point being of a particular class. So we just sum up all those probabilities and divide that by the total number of data points. Okay? So I hope this is making sense. It's just carrying forth what we did earlier for Gaussian Bayes classifiers, where we knew the labels, to now having a weight that each point comes from a class. Okay? So everybody okay with this? Let's look at an example, and hopefully this will become even more clear then. So here are some data points. Okay, so first let me tell you what is shown here. Every circle represents a data point, and the colors it represents shows essentially the expected label at that iteration. So it shows the probability that, for example, you can think of it as a pie chart, which indicates the probability that it belongs to, this point comes from the green component, or the red component, or the blue component. So some of them you can see there's a lot of uncertainty that they might come from each class with equal probability, while other ones are more pure. So some are very impure, others are pure. Right? That's what this is going to show as the iterations progress, and you will see that how these probability estimates improve. There's going to be, we are modeling this with a mixture of 3 components. So there are 3 means, mu1, mu2, mu3. These are randomly initialized to some values. And 3 covariances, sigma 1, sigma 2, red one, and sigma 3, the blue one. And they are also randomly initialized to some values. Okay, so just some random matrices. And yeah, as I said, the color here for each circle is going to denote the probability that that point is was drawn from that component. Right? So this is the initialization, right? And as we continue, we'll see that after one iteration, how these things improve. So that's how the probabilities of the points change, right? You can see already that some of these ones, for example, are now, oops, wrong way. They are inclining more towards red, right? These ones are becoming more bluish, and these ones are greenish. And you also see how the covariance updates have changed after running one iteration of E and M steps. All right? And we can keep going forward. That's after second iteration. After the third iteration, you can already see that the green points are forming their own cluster, and the covariance is also sort of aligning more and more with those points, the covariance estimates. And the 3 components are becoming sort of more clear. And as we keep going, that's 4th iteration, 5th, 6th. And at 20th iteration, you see that there's a very nice, all of the estimated covariances look good. The means, of course, are in their center. They look good. And the points are almost quite purely assigned to a cluster. Not completely. You can still see some little bit of green and so on there. But it's a very nice assignment of the points to these 3 mixture components. So that's what EM would look like in practice if you ran it. Right? You're estimating the expected label of each point and then using those expected labels to compute the estimated means, the covariances, and prior mixture proportion of each class. Right? So this was a toy example. Let's look at some real data sets. This is a data set which corresponds to assay, which is like taking essentially different molecules and looking at certain properties here, let's say in general. And you can see that it's there's no easy, if you just looked at those blue points, there's no easy model that would come to your mind on how to fit it. But you can use a Gaussian mixture model. And you do have to specify how many components you're using. Right? So here there were 6 components that were chosen. And after you run EM, you can see that you have these, you can sort of model this data by putting 6 bumps essentially of with different means and different covariances around. Right? And it provides a pretty nice estimate. This is how the resulting density estimate looks like. So this is P of X after you have done the training. Right? This is P of X using, again, that's just summing over each class, the prior probability of the class times the probability that a point came from that class. Right? So this is the overall density, how it looks like. And as you can see, you are seeing that there are some places which are modeled nicely by Gaussians and the other ones where these probability contents overlap a lot, but it's providing a nice or very complex kind of representation. more generally, you can do classification using Gaussian mixture models. And how you do it, essentially what we mean is that each class, if you look at its distribution, may not be Gaussian. So we are not talking about doing Gaussian-based classification here. What you're talking about is that for each class, the distribution of points is very complex. So you actually use a Gaussian mixture model to model the density in each class. Okay? So for every class, you could have the data be modeled by a Gaussian of 6 components or 5 components or whatever makes sense. Okay? So I hope you don't confuse this with Gaussian-based classification. What we are doing now is, even though initially I referred you to it, what we are doing now is we are saying, so we have this P of x given y, right? For each class, so say y is I. Now let me call these y primes. These are not the hidden labels for each component, but these are the classes. And every such P of x given y prime is a particular class can be modeled as a Gaussian mixture. Right? So there's a certain probability. So this is summing over all components of that class, a certain probability of that class. So this could also potentially depend on which class you're talking about, and times whatever distribution you assume, say a Gaussian, with a particular mean for that class, and for that component and for that class. So there are sort of almost 2 indices that will index all of these. Does that make sense? So think of just the blue data, I'm fitting a mixture model to it. Just the red data, I'm fitting a mixture model to it. Just the black data, I'm fitting a mixture model to it. And then using all of these jointly, you can still do classification, right? You've just replaced a single blob for each class with a mixture of blobs for each class. And you can get much more complicated decision boundaries. So for example, in this setup, where we modeled each class with a mixture model, this is how the resulting Bayes classifier looks like, using the Gaussian mixture model as the class conditional densities. All right? Did everybody follow this example? Any questions about it? Okay. All right. Yep. See one.
Isn't that really similar to a classifier with like Gaussian kernel in terms of decision boundaries?
Is it similar to a single Gaussian? You're saying, or doing Oh, a kernel classifier.
Kernelless, yeah. The functional form is similar,
Yeah.
right? Like but it's not, you get the decision boundaries by a very different process, right?
Yeah, the decision boundaries will be completely different. Maybe the complexity of the boundary itself might maybe be comparable, right? Because you're getting it using the same.
The functional form is the same, right?
Right,
for
yeah.
each class, you have a sum of kernels centered on points,
Right. Yeah.
It's just that, so for each class, just like with a Gaussian kernel classifier, you would have a sum of Gaussian kernels centered on points. But here, the points are not individual training points, whereas for let's say a Gaussian RBFSDM, they would be. Here, we're adapting the covariance matrix separately for each class, so that's a little bit different.
But actually, this is very parametric also, right? You're choosing k beforehand, right? There you would have, if you set like k to be n, the number of points per class, then maybe it would be more similar to the...
Right, although even with that, right, the optimization would give you something.
So the answer would still be different, but at least the form of your classifier would be, or the equation for the boundary line would be very similar.
But like vaguely what the kernel, what the class boundaries look like, it's the same class of functional form, so you wouldn't be able to, at least I probably wouldn't be able to tell by looking at it which type of optimization somebody could use.
Yeah. Right. But that's a good point. That in general, I think if you let like k, for example, scale with n, then you are sort of doing essentially a kernel-based approach here. Yeah. Right. Any other questions? Okay. All right. So hopefully now that you have seen how, at least impressive in some sense, in practice it can be, EM algorithm is used actually quite, it's probably one of the most widely used algorithms so far in practice. And having seen some examples, hopefully you're ready for the more general form of EM algorithm that we'll do, which basically will imply not only using it for the mixture model setting, but you can use it anywhere you have some data that's hidden and you're trying to still maximize the parameters under some model. Okay, so a particular example of that which we'll get to maybe towards the end, a place you have seen that happen is HMMs. You have some hidden states, right? You don't know, and you have observations, so you can still try to maximize the likelihood of the observations, but you don't know the hidden states. So if you were to learn the parameters of a hidden Markov model, how would you do it? You would do it using EM. Okay, so we'll get to that again towards the end, but that's just another example of a problem where you have hidden some part of your data that's hidden. You're trying to maximize the probability or likelihood of the data that you see while trying to infer. So as an intermediate step, you'll impute the hidden values, use those to update the parameters, and go back and forth between these two. Okay, so it gives you an algorithm to try to maximize the parameters even when you have hidden variables. That's generally what EM algorithm is about. So we'll try to look at it in a much more generality right now. All right, so here is how we look at it. So the essentially the generalized EM algorithm is you have some part X, say, of the data that's observed, Z is missing. Okay, so in mixture models, the samples were observed and the labels were missing. In a hidden Markov model, your observations from each state is the data that you observe. Z is the value of the state variables that is missing, right? You don't get to observe that. And you're trying to fit the parameters, right, of whatever model captures involves X and Z, right? So you have some parameters which we'll call theta in general. So these were the means, the covariances, and the mixture proportions for mixture models. What would be the parameters for a hidden Markov model? Anybody remember that? The state transitions and emissions and one more. Initial probabilities, right. So yeah, so those would be your theta then, right? Okay, so yeah, you were all well prepared for the midterm. All right, so yeah, now we are trying to actually estimate all of those things just given the observations, right? Your emissions, your transition probabilities, your initial probabilities, all of those. So all of those we'll call theta. D will be the data that we observe, which in this case we are calling it as X's, right? So we maximize the log likelihood of the data we observe. We call it marginal likelihood because really you could be optimizing over the hidden variables also, the joint likelihood of X and Z, but you don't get to observe Z. So we have again log of, because all the data are IID, or not IID, but at least independent, we can write it as the product over the probability of each one of the data points, xj, given the parameters. We can, of course, interchange the log and the sum, and the product by making it a sum outside, right? The key difficulty again comes in because we have to marginalize out over the hidden variables, right? We are only maximizing the marginal likelihood of X, whereas we actually have a model for X and Z together. So we need to marginalize out Z because we didn't observe it, right? And that's what makes it complicated, that you don't get a closed form expression for your parameter updates anymore if you just try to differentiate this with respect to theta and try to solve it. All right, so how do we maximize this marginal likelihood? We're going to do it using EM. So how does EM go about doing this, and why do we end up with the solutions we talked about earlier for Gaussian mixture models? Why is the solution that you just think of these weighted data points as weighted by the probability of belonging to each and do the ML update? We'll come to that, okay, as a solution of what we just do next. So this is how EM goes about it. You want to maximize the log likelihood of your observed data, which is just X's, so you marginalize out over the Z's, right? What we actually do is, instead of directly maximizing the likelihood, we are going to maximize a lower bound on the likelihood. Okay, that's how EM is going to approach this problem, and we are going to maximize that lower bound by essentially using coordinate descent, or ascent in this case. All right, so how do we do that? So we first of all take exactly our marginalized likelihood, and we multiply and divide by some q, which I'm calling as q of z given xj. Right? I'm just multiplying and dividing by that. And I'm doing that so we can come up with a lower bound that we can think of as a function of two variables on which we can do coordinate ascent. All right? Then we are going to use something called Jensen's inequality. I think I briefly referred to it in an earlier lecture. But here's what it is. So it holds for, say, concave functions, right? And what it says, so if you have a concave function, it essentially looks like this, right? And essentially what it says is that if I take 2 points, and I look at So x and y are my two points. And if I look at a point in between x and y, so this point, which is given by some ax plus 1 minus ay, where a lies between 0 and 1, right? So it's some point in between x and y. Then the value of the function at this midpoint is larger than the average of the values of the function at x and function at y. Does that make sense? So if it was convex, it would be the other way around. If it's concave, it's essentially saying that the function lies above the line connecting the 2 points, right? So the function values between these 2 points lie above the line connecting them. Okay. So we can use this inequality, and it tells us here, for example, because log is a concave function, it says that log of, if I look at something like this, sum of some probabilities times fz, probabilities are between 0 and 1, so you can think of those as a and 1 minus a if there were only 2. Right? So we are taking some f of z, which you can think of f of z is x and f of z prime is y, for example, right? And we are interpolating between these values. Then the log of that sum is greater than the sum of the logs. All right? That's how we'll use Jensen's inequality, that log of the sum is bigger than the sum of the logs. All right? Okay, so with this very useful tool, what we can do is essentially it helps us move the log inside the sum. And that's really nice because that sum was what was causing us the problem as far as trying to maximize it and getting a closed form expression.
Should there be a second log in that second side of the
Here? Before P of z? Yeah. No. Because again, think of these P of z's as the a and 1 minus a's, right? These are probabilities. And so what we have is we have the probability times log of one value. So if z was only taking 2 values, this would be P of z times log f of z and P of z prime times log of f of z prime. Think of those points exactly, f of z and f of z prime as x and y. Does that make sense? All right, so yeah, it's essentially helping us move the log inside the sums, and that's what's really helpful. And not only inside the sums, it's actually moving it all the way. You can bring out the P of c, actually, even outside the log. Everybody follow this? Yeah? Yeah. So yeah, actually here, yeah, I haven't told you how to apply it to this. We'll think of this as P of z and this is f of c in case that was the question. Was that? Okay. Yeah. So I just told you how Jensen's inequality is going to help us by moving the log inside. Particularly, we'll think of this q as the p's I've been talking about here, and this thing as the f of z. All right? And so what we get using this rule is that now we can move the log essentially right here before this fraction. Right? And that's the lower bound. Okay? So now we have a lower bound. We'll actually call it as a function of theta, which are our parameters, and q, this distribution that we introduced. And the reason we did this is now we think of these as the 2 coordinates that we are going to do coordinate ascent on. Okay? So we want to maximize the log likelihood. Instead of that, we'll maximize a lower bound on it. And the way we are going to maximize the lower bound is keep one theta fixed, maximize over q, keep q fixed, maximize over theta, and keep on repeating this process. That's coordinate ascent, essentially, right? All right. So EM first lower bounds the log likelihood with this function that we just derived. And the E step is going to fix theta, the set of our parameters. You initialize them randomly, then you fix them, and you maximize this lower bound over q. And we'll see that q is nothing. So q is just going to be, it has something about the expected value of our hidden data, right? Z was the hidden data. So it's essentially a distribution over that hidden data. Right? So first we are going to impute those assignments of the hidden variables, that's q. So we are going to maximize over q and update those. And the m step is going to fix those assignments and now update the thetas, which are our parameters. So now we are going to maximize this f over the parameters, keeping q fixed. And we'll iterate between these two steps. All right, so why does this procedure converge, first of all, before we even get to what the E and the M steps look like? So E step is maximizing a lower bound on the marginal likelihood, right? So it never decreases the marginal likelihood because you're always maximizing a lower bound on it. Similarly, the M step is also maximizing a lower bound, right? So we expect that we'll never actually decrease the likelihood Why do we expect convergence, right? So first of all, yeah, what is this telling us? Is just that the first step, so say we start at some initial values of theta in q, right? We have some value of f of theta in q. The E step is finding a q that is only an upper bound on it, right? It's only increasing this f value. And the M step is further increasing the value, right? So we are going from between one step to another, we are just increasing the value of this lower bound, right? So at every iteration, which means one E and one M step, we have only increased our value of the lower bound. And we know that the likelihood is always bounded, right? Likelihood can't be unbounded. So we'll eventually reach a local optima. Does that make sense? Because the marginal likelihood is bounded, you're always going on increasing it. At some point, you're going to hit the maximum value, at least a local maximum. And therefore, EM always converges. Okay? So if you want to think of it pictorially, say this is your likelihood, marginal likelihood function, right? The P of d given theta. You wanted to maximize it. You wanted to find the parameters that maximize it. We can't solve for it directly, but we essentially put a lower, we are going to use a sequence of lower bound functions. So for every theta that we start off with, think of this as just theta. We come up with a lower bound and we maximize it. We find the value that maximizes it. Again, we come up with a lower bound, right? And we again find the value that maximizes it, and so on. So we are going to build essentially a sequence of these lower bounded functions that will finally get us to, it's always going to improve the lower bound. So it's always going to improve actually the likelihood, and it will get us to the maximum. Often it doesn't get you to the maximum, right? Because the functions often look like this. It has a very, it's not a single, it doesn't have a single maximum likelihood. So there are local maximas. And so depending on where you start from, you could start very nearby, but you could end up at different local peaks. All right? So EM always converges. It may not converge to the global maximum likelihood. It does converge to the local maximum likelihoods. So often you use random initializations of the parameters, right, that we talked about initially. You do it many, many times and choose a value that gives you the largest likelihood. Just like k-means, right? In k-means also, we needed to initialize our centers, run many random restarts, and then pick the value that gives you the best k-means objective. All right, so let's look at, we know that it always converges, and we sort of have this general formula for how to get to the E and the M steps in the general case. But let's look at what these E and M steps actually correspond to. We have a particular form for F, right? We have a lower bound that we derived. So we can look at what those steps are formally. So the E step, as we said, we are going to fix theta, say at some value theta t, and we are going to write the F as a function of Q and then maximize over Q. Okay? So this is just writing from before the value of F that we had derived. Okay? So if you go a few slides earlier, we had come up with this lower bound, right? This one. So I'm just rewriting. I had defined this to be F. I'm just rewriting this, where now we are holding theta t fixed, and we are thinking of it as a function of Q that we'll maximize over. All right. So let's get to our E step. Yep. So here's the E step. We are writing out that F just by definition. And notice that what I've done here is now just rewritten this joint likelihood of Z and XG, X as Z given X times the probability of X, right? You can do that using Bayes' rule. And now noticing that I can split it up into log of one term times another term, right? So it's log of A times B. I can write it as a log A plus log B, right? So the first part is just the same as before. And the second term, I'm going to pull it off as a plus log B. Did people follow this? Right? And you'll see that this first term, if you have encountered it before, is actually the KL divergence between the two distributions, P of Z given X and this Q distribution we defined. So this expression is exactly the KL divergence between these two distributions or the negative of that actually. And the second term, you see that the only thing that depends on z is just this q. And it's a distribution. So if I'm summing over z, that has to sum to 1. Right? So all I'm left with is this whole part sums to 1. I'm left with the sum j equal to 1 to m of the log of the distribution of x's, which is just the log likelihood of the data. Right? That's the same quantity I have on the left-hand side here. Right? So what we have shown is that this lower bound is actually just, we have lower bounded log likelihood of the data by log likelihood minus the KL divergence between two distributions. Okay? So if I now say, well, let me maximize this lower bound over Q, what should the maximum value be? So for this, here I've just repeated what we just did. We showed that this lower bound is nothing but the negative of the KL divergence between the two distributions plus the log likelihood of the data. And the KL divergence is always bigger than or equal to 0. So it's a measure of how different two distributions are. And it's always bigger than or equal to 0. It's equal to 0 if both the distributions are the same. Yeah. So when is this bound maximized? When the KL divergence is set to 0, right? It's always positive. And KL divergence is 0, as I said, when both the distributions are actually the same. It's a measure of how different distributions are. So it's 0 when they are the same. So it actually tells us that the solution, what Q maximizes the lower bound is when Q is equal to P. Right? So the solution, the E step is just that your Q distribution is just the probability of the hidden values given xj's. So if you were doing this for the Gaussian mixture model, it exactly tells you that the E step is you compute the probability of your observed, of your hidden, of your class labels, right, mixture assignments, given your data point. That's all you're doing in the E step. Right? And it's a formal justification for it. So that's the E step. What does the M step correspond to? So M step also looks at, now you're going to fix, this is just the E step. I guess there was one more point I wanted to say about it. Right, so the solution is just that your Q is just the probability of the hidden values given the x's. That's just computing the probability of the missing data given the current choice of data. And yeah, I wanted to say this, that notice that you are actually realigning your lower bound with the marginal likelihood. The reason being, we had the marginal likelihood, we showed it's lower bounded by the marginal likelihood minus something. And we just, by maximizing, we just set this to 0. So what we have actually shown is that our f at the value of Q which maximizes it is equal to the log likelihood of the data. Right? So when we are maximizing the likelihood, we are actually getting to the, or when we are maximizing this lower bound on the likelihood, we are actually getting to the likelihood. We are just realigning our lower bound to match up with the likelihood. That's what the E step is doing. Right? Okay, so what about the M step? So the M step now fixes Q at the value we just computed, Q t plus 1, and we are now going to maximize f over theta. So here's just rewriting f again, this time writing Q as Qt plus 1 because we are going to hold that fixed, and we are leaving theta as is because that's what we will maximize over. And now we'll just use a rewriting trick to now rewrite it as follows. So what we did was we wrote it as, thinking of this as log of a over b, we wrote it as log a minus log b. Okay? And when I pull out the minus log b term, I just get some q log q, right, or negative of that, negative some q log q. That's just the entropy of a distribution. Right? You've seen it before. So what we end up with is this term, which just corresponds to the numerator here, and plus m times the entropy of that distribution. The reason we wrote it like this is because we were going to maximize this lower bound, holding q fixed and maximizing it over theta. Since q is fixed, this term is fixed, we don't have to worry about that, and we are simply maximizing this part over theta. Okay?
Wouldn't it be a separate entropy term for each training point j? So not m times it, but just the sum over j. Yeah, so I believe in such, and they won't be the same necessarily. Right.
Right.
I mean, it doesn't matter because it's about to go away.
Yeah, yeah, right. But you're right. Okay, so yeah, I guess for mixture models, would this be okay? Or yeah, I was trying to do it. Or no, in general, it can be
it's just
different. Yeah, it's different for each data point. So yeah, so it's better to write it as sum over j of this, right? Yeah, instead of n times that. Yeah, in general, yeah, the distribution is going to be different for each data point. Yeah, that's a good point. Right, but anyways, we don't care about this term because we care about we are holding q fixed and maximizing over theta. So this term doesn't matter. We're only going to maximize this term over theta. And what is this term? How do we understand it? Well, let's flip the order of the log p and the q, and then it will become something recognizable. Once we notice that this term is nothing but, so I flip the z's, this order of the summation, and the log p and q, all valid operations, right? Now, why does this make more sense? Because if I just look at this part, that's just the likelihood, log likelihood as if z was observed, right? So if z, say your class assignment was observed, you would just be maximizing the joint likelihood of the labels and the features, right? So you would just be doing maximizing this. That's just your log likelihood as if z was known. And now, because you don't know z, you're estimating the probability or the expected value, if you want to think of it, of z. And now you're just maximizing this expected log likelihood. Okay, so this whole term you can interpret as the expected log likelihood with respect to the assignment distribution of your hidden variables. Right? So that's exactly what we do. We are going to now, the m step is going to do maximum likelihood, but it's going to do this maximum expected likelihood. Right? Maximization. And that's what leads to, so this is just rewriting what we just, the lower bound we showed is equivalent to that. And so our m step is just going to be update your parameters to maximize this expected likelihood. So that's why our second step, the m step in Gaussian mixture model update, was you take all your data, the maximum likelihood estimate would be just the sum, for example, for the cluster center would be the average of all the points that are assigned to it. Now you will have, because you're maximizing expected likelihood, you also take the probabilities of each hidden class into account. And you count each data point as many times as proportional to the weight, the probability that it belongs to that class. All right? So again, wherever you're using counts, you would use expected counts instead of that, essentially. Where the expectation is with respect to this distribution that you have computed. All right? So here's essentially summarizing EM as a coordinate ascent method. It's very, very general. As we said, you can do it for whenever you have some hidden variables z and some observed data x. You are essentially doing the E step, which is maximizing this lower bound, which is essentially just equivalent to computing the probability of your missing data z given the observed data, right? So it's just P of z given xj. And for the Gaussian mixture model example, this was just estimating the probability of being drawing from one particular component given xj and your current estimate of the parameters. And the m step just computes the estimate of theta by maximizing this expected likelihood. Okay. All right. So this was quite a lot, but this is the general EM strategy, and you can really use it to apply it to Gaussian mixture models or to, as we said, like hidden Markov models if you want to learn the parameters of the hidden Markov model. All right. So let me summarize EM. So we showed that it's a way of, again, maximizing the likelihood when you have certain hidden variables, and you can break down your problem into first estimating the hidden variables or computing the probability of the unobserved things, and then using that to find the maximum likelihood estimate of your parameters. You do this by these two steps, which are like coordinate ascent on this underlying, on a lower bound on your marginal likelihood. And yeah, in the M step, you're just maximizing the lower bound. In the E step, as we saw, we are actually making the bound equal to the likelihood. And because it performs coordinate ascent, if your function underlying log likelihood tends to be convex, you will achieve its maximizer, but in general, you only achieve a local optimum, so a local maximum. Right. Okay, so it's extremely popular in practice, and let me quickly, I guess, I think I did throw in a few slides again to remind you of how you could use it for learning hidden Markov models. So hidden Markov models, as I think you're all fresh with these concepts, essentially correspond to a sequence of hidden states, and a particular observation corresponding to each state, right? And the parameters here are the initial probability of starting in a particular state, the transition probability of going from one state to another state, and the emission probability. What's the probability that you observe something given the value of the state, right? And if I only gave you a bunch of such observations, and I wanted you to learn all of these parameters, how would you do it? You would use EM. Okay? So the learning problem would be, again, as I said, like here are the parameters, and you're given this observation, and you're trying to maximize the likelihood of your observed data given theta, which is this set of parameters, initial, transition, and emission probabilities. And you have this hidden variables, which are the state sequences. So we are going to use EM. We are going to fix the parameters, find the expected value of the state assignments. Actually, you should know how to do that. Do you remember? You computed the probability of a state ST being equal to something, right, given the observations. That's something, that's an inference question, right? So if you were given the parameters, you know how to compute the probability of a state, right, given the observations, the posterior probability of the state. That's something you've learned, right? So you know how to do the E step. And the M step is now going to be, you're going to fix those expected state assignments and updating the parameters. So we can quickly look at the M step. Hopefully you all know the E step. So yeah, that's just a side, because in this case the observations are not IID. You can't just write it out as product over all your observations, right? So each observation depends on the previous one. Unlike the Gaussian mixture model, there's a slight difference here. But you can still use the EM algorithm to do that. So here's how the EM algorithm looks like for learning the parameters of a hidden Markov model. You start with a random initialization of your parameters. Once you know the parameters, you can compute. You can find the expected state assignments at a time t. What's the probability that state assigned to is I, given the observations, which is O1 to OT, right, and your current parameters. And you can also compute what's the probability that state at time t minus 1 was I and that t was j. Right? These are just two inference questions once you're given the parameters. So hopefully you should all know how to do that. Right? And what's the M step? So M step will depend on these few quantities that I'm just defining. So you can think of, if I take this value and I sum it from I equal to 1 to t, that's essentially the expected number of times you visit state I, right? I'm computing what's the probability that the state at time t was I, and then I sum over all such t. So I'm essentially talking about what's the expected number of times I visit state I, right? And similarly, if I sum over, if I also sum from only t equal to 1 to t minus 1, so not all the way up to capital T, the last point, then I'm summing how many times did I transition from state I into something else, right? If I just don't count the last one. And if I do the same for this second variable, which is computing the probability of two consecutive states, then I get the expected number of transitions from state I to state j, right? So once we have this, we can use these to update our parameters, right? Because what are our parameters? That's the M step, right? So our initial, one of the set of parameters is just the probability of being in the initial state I. That's just talking about actually what's the probability that state at time 1 is I. So that's just gamma I1, right? So once you have done the E step, you have gamma I1, which is the probability that state at time 1 is I. That's your estimate of the initial probabilities. The transition probabilities, you can estimate, it's the probability that you transition from state I to state j, right? That you can just count how many times did you expected number of transitions from state I to j times how many times you actually left state I, right? So these are the two quantities we have defined above. You just take their ratio, and that gives you an estimate of your probability of transitioning from state I to state j. And you can do something similar for counting the emission probability. So emission probability is the probability that you were in state I and you observed k. Your output OT was k. You just count amongst all of your steps how many times did you output k, and you multiply it with how many times you left state I, right? So you're essentially counting how many times you left state I in your data and you observed k as the output. You just count that total number of times, divide by the total number of times you were in state I, and that gives you the probability of being in state I and outputting k. Okay? So these are the steps in your EM algorithm, and it's known as Baum-Welch when we talk about it in the context of learning the parameters of a hidden Markov model. Right? So this is another example of using EM. All right. So before we go on to the next topic, I just wanted to mention, if we have time, I just wanted to mention a connection between hidden Markov models and mixture models. Do people see any similarities or differences? So this is just reminding you what in an HMM, if I were to talk about what's the probability of my output, which is the observed values, right? What they look like, it's just the probability of being in a particular state and transitioning from, and outputting OT given you were in that state, right? I can sort of write it like this. And essentially notice that this is very similar to a mixture model, except that in a mixture model, what the current value of which component you were drawn from, or in this case which state, that does not depend on which data point it is, right? So here the different data points correspond to the different t's, right? You just have, with certain probability, you pick one component and then you draw a sample from it, right? When we are talking about this, we can use HMMs to define this called what is known as dynamic mixture models. You are picking a state and then drawing an observations from it, but the state you are picking can depend on previous states. Whereas in a mixture model, Gaussian mixture models, when we are drawing from one component, that draw did not depend on which component was picked earlier, right? So this gives you a way to think of HMMs, or using HMMs to define a dynamic mixture model essentially, right? So if you want to think of it pictorially, here's what's happening. You have some data, and in a static, like a Gaussian mixture model, you sort of have this representation where your state is which component you picked, and then there's a certain probability of observing the output from that state. But all the states are independent. There's no connections between the different states. So using the plate notation, I've just written an n here to say you can replicate it. If there are n components, you can just replicate it n times. Whereas here, you're picking a state, but the state you pick or the component you pick can depend on what were the previous components you have picked. So this is, now you can think of it as an HMM. You pick a state or a component, you draw a sample from it, but now you can pick the next component based off of what was chosen previously using your transition probabilities and so on. So you get a dynamic mixture model instead of a static one, essentially, where which component you draw from can potentially depend on previous things that you have drawn from. All right. So any questions on this? So hopefully you've seen EM. We did a bunch of math, which may or may not have made sense, but it gives you a general recipe to try to apply EM to any problem where you have missing data. And we saw two examples of that, mixture models and the HMMs. And hopefully you'll be able to use it for more things. All right, so with that, let's take maybe 3 minutes break, because I know this was quite a lot, before we start talking about PCA, which is a relatively small topic. So yeah, if you want to just go out or just take a break. All right, so let's start back on the next topic, which is fairly short and pretty useful. So this is principal component analysis. So I think in the spirit of doing things on unsupervised learning, we have looked at density estimation, we have looked at clustering or mixture modeling, and we also talked about, well, you might in some cases want to not keep track of all the features that you have with you and do some kind of dimensionality reduction. Maybe there are too many dimensions to keep track of, and what is a useful way to try to reduce that dimensionality? And either compress your data, or maybe you can even do denoising using it. We'll see that principal component analysis gives us a way to do all of that. So we'll talk about motivation, the algorithm, and then some applications. Particularly, as I said, PCA you can think of it as using it for 3 potential reasons. One, to make sense of your data just visually. If you have high dimensional data, you don't know how to plot it and look at what structure it represents, right? So PCA gives you a way to visualize your data. It also gives you a way to compress your data, because then you can throw away, once you have found some meaningful low dimensional representation, you can just keep that low dimensional representation and throw away all the original high dimensional features. So it gives you a way to compress your data. It also gives you a way to do noise reduction, because very often the part that you're able to compress is some important signal in the data. Noise is not something you can compress. So if you are compressing, you're sort of leveraging the signal, and if you throw off the higher dimensions, only keeping the lower dimensions, you're sort of throwing off noise. Okay? So we'll talk about these in more detail, but these are 3 motivations at least for looking at principal components. And as a specific example, think about, say you have some data set, and this is actually not even a very high dimensional data set per se, right? I mean, if you're all playing with really large data sets in your, or many of you are at least, in your projects, and this is really not that large. 53 samples, blood and urine samples from 65 people, fairly sort of small data set, but how do you visualize it? It becomes pretty challenging, right? So I can try to write it as a matrix where I have, here are the different subjects or these patients, so I guess we said 65 of them, and 53 values of blood counts or different urine samples, some properties about them. And just by looking at a matrix, it's hard to see what kind of structure exists, right? Is there any correlation between the different features? I haven't even written out all the features. There are 53 of them. Or between the different patients. It's sort of a bit hard when you have a table like that. You can try to plot something like for each, you can have for each patient, right, some kind of a curve which represents their representation in a 53-dimensional space, right? So I can plot the values of the 53 features for each patient as a different curve, right? Which can tell you something about how these values are correlated, but it still is hard to compare the different curves together, right? So you can't compare different patients very easily. You can do the other way around. You can represent for every feature, you can look at how the different patients, right? So here are the 60 patients, 60 or so, and how their values for each feature look like. But now you're missing out on the correlation between the different features, right? So you can either look at the feature space or the person space in some sense. And it becomes hard to, once you have 53 such pictures or curves for each of the features, it's hard to make sense of that, right? Well, other things you can try is, well, why not look at feature by feature? So here are my data points. I just picked 2 features. So features here are again the values in 2 tests, some blood work and some urine samples. And you can see how the people are placed in this 2-dimensional space, or you can maybe do 3-dimensional, but then you're stuck there, right? You can look at all pairs, all triplets, and so on, but it still doesn't give you a holistic picture of how are these points placed when you are talking about your large feature space, so all 53 dimensions, right? So how do we visualize our data while taking information from all of these dimensions into play, right? So that's what principal components is going to be a way. We are essentially going to look at a representation that's better than just these, thinking of the features as the axes, right? So we'll think of, is there a way we can maybe only save linear combinations of features that's more meaningful than the original features, okay? And is it really necessary to use all of these? Because if there are strong correlations, right? So suppose here's a feature x1, x2, and all the data literally lies along a line. Then it's saying that maybe x1 and x2 are not that important. It's only this new feature, which is some x1 plus x2, or maybe a times x1 plus b times x2, that's really of importance as far as describing this data set goes, right? So maybe we only want to keep this combination of these 2 features, which have very strong correlation in the data, right? Or we might think about what's the smallest subspace that captures most of the information of our data. And we'll talk about what we mean by information more formally with principal components. But you're essentially saying, can I take all my data, throw away a lot of the dimensions, and still hope to capture something, some information which is still preserved as much as possible. And principal component analysis gives you a way to answer all of these questions, right? So what does it correspond to? So let's look at some algorithms for doing PCA. So first of all, what PCA is trying to do, it's saying that you want to come up with the orthogonal projection of the data. So the data here are actually just the red points. So you have 4 data points. We are trying to find their projection onto a low dimensional space. So the low dimensional space here would be this purple line, right? You're trying to project these points orthogonally, perpendicularly onto it, such that what property should this linear subspace have? It maximizes the variance of the projected points. So if I take my original points and I'm projecting it onto this space, then I get these green points. And if I look at the variation of these green points, that's maximal along this direction. Okay? I could have taken any other curve, any other line, so say like this, and I could have projected the points perpendicularly onto it, but the projected points will have smaller variance. So I'm trying to find a line such that if I project all of these points perpendicularly onto it, the maximum variance is captured. So here one information you're trying to preserve about your data points is that the variance of your data points should still be preserved maximally, even if I replace these two original features with this new feature. In this case, it's a single feature, right? Because it's a 1D line. But more generally, this could be, you could be in 3D trying to come up with a 2D space, or you could be in 10,000 dimension trying to come up with a 100 dimensional subspace. You can extend this idea. But we're trying to find that one subspace of whatever lower dimension we specify, in this case a 1-dimensional subspace in 2D that maximizes the variance of the projected data. Another notion could be that instead of maximizing variance, you might say, well, we want to minimize the mean square distance between the data points and their projections. So I want to minimize the sum of all of these blue lines, which is the distance from every point to its projection. So I want to find a plane such that if I perpendicularly project the points, I minimize the sum of all these distances between the points and their projections. Now these seem like two very different objectives. Turns out they have the same solution. The same subspace both maximizes the variance of the projected data as well as minimizes the mean square distance between the points and their projections. And that's the subspace of interest, which we'll call as the principal subspace, and it's the basis vector that span that subspace are going to be the principal components. Okay? So PCS serves two purposes. It finds a subspace that maximizes the variance of the projected data or minimizes the mean square error between the points and their projections onto this. All right, so yeah, as I said, like you could think of it more generally as some 2D in 3D or 10D in 100D or 100D in 10,000D, whatever makes sense for the problem. So given data points in a d-dimensional space, you want to project them into a lower dimensional space while preserving as much information as possible. In particular, we are going to focus on choosing a projection that minimizes squared error or maximizes the projected variance, right? As we talked about. So principal components, they are going to be the first one. So principal components, as I said, are just a basis for this principal subspace of interest. And in fact, what we care about is that the first principal component we pick, which is going to be a single vector, is the vector along which direction the points have the largest variance. So if I only choose this 1-dimensional projection, then the points have the largest variance. Then each subsequent one that I'll pick, I'll want it to be orthogonal to the previous one and have the largest variance amongst the residual points. What I mean by that is if I took my original points, I projected it down onto the first direction that's most relevant, and if I look at the spread of the remaining points, now if I want to find another direction which captures the variance of this projected points, right? And so on. So we can extract as many, we can keep on extracting PCA vectors. First one captures largest variance, second one captures largest variance of the projected ones that are projected off of the first principal component, and then find the next one which is projected off of the first and second principal components, and so on. All right. Another important point is we would want these PCA vectors in some sense to originate from the center of our data. Okay, so when I show you a picture next, it will make sense. So what we have in mind is something like this. You have a 2D, say here a simple Gaussian data set, and you can see that there are two features, but they are correlated strongly, right? So our first principal component, we want it to start from the center of the data and correspond to a direction which captures most of the variability. As you can see here, it does, right? And the next one we want should be orthogonal to this direction, but capture the variance in the residual data. So what I mean by residual data is you take all these data points, project it onto the first one, right? Now you have collapsed them along this line, right? Or off of it, you have collapsed them like this, right? And now you look at which direction captures the maximum variance in that data after you have projected it off of that original space. All right? So how would you get to such a subspace? Well, formally you can just write down something like this. You can say that first I'm going to center my data, right? Because I want these PCA vectors to start from the center. So you take all your data points, you subtract off this empirical mean, right? And then we are going to compute this principal component vectors such that if I take all my data points xi and I project them onto w, which is this direction, right? Then w transpose xi is your projected data point, right? I'm asking that these directions have unit norm. It makes sense, right? Because I can always scale up that particular vector and just make the variance larger and larger that way. So I'm going to force all of them to have unit norm. And then W transpose Xi is I just took a data point and I projected it onto this subspace. So that's my projected point. I square it up and I average all such values. That's just the variance of the projected data points, right? And I want to find a W that maximizes this projected variance, right? So solution to this problem will give you the first principal component. Okay, it's going to be the direction which maximizes variance of the projected points. Okay. And you can talk about getting the second one, which will be defined similarly, except that we are finding the W onto which not the original points, but the original points minus their projection onto the first component, that their variance is explained well, right? So essentially what we are doing is, so here's W1, that's the first principal component, let's say, of this data. Here's a point X, right? If this W is unit norm, then I can just do X transpose W, gives me the length of this projection. And what's my new data point? It's that length times this unit vector in this direction, W1, right? That's my new representation for that data point after doing the projection. So I'm saying let's take that projected data point, subtract it off of the true data point, right? That gives you this residual. So now the X has become X minus X prime, which is this residual. And I'm trying to now explain this residual variance using a second principal component. All right? So I'll now find another vector which maximizes this residual projected variance, and so on. You can find the kth principal component as the one where you're maximizing, you're again projecting onto W or trying to find such a W of the original data point minus its projections onto the previous k minus 1 data points, right? So now you're, for example, trying to find W2, where you have subtracted off, here was your original data point X, you subtracted off its projection onto W1, right, and also onto, say, W2 now, and you're trying to find whatever maximizes the residual variance. Okay. So ideally that's what you would want to solve. How exactly would you solve it? So let's go back to the first one, right? How did we find the first principal vector? We said, well, we want to maximize this quantity. Now it looks kind of like a hard optimization problem, but you can see that all that this optimization is doing is saying find maximize over vectors W's that have norm 1 by m, sum I equal to 1 to m, W transpose Xi squared. I'll just write the squared as Xi transpose W, right? Because it's a scalar, W transpose Xi, I can just repeat that, right, as Xi transpose W. And this is nothing but, actually I can write it like this, W transpose 1 by m, sum I equal to 1 to m, Xi transpose times W, right? So you see something very familiar, right? All we are doing is we are saying find the direction which maximizes W transpose sigma W, where sigma is just your empirical covariance of your data, right? Because your data is already centered. So Xi transpose is just the sample covariance, right? And what's the solution to this? If I'm saying find the unit norm W that maximizes this, that's exactly the first principal component of sigma. Or the first, that's the first principal component. It's equivalent to the first eigenvector of sigma, the eigenvector corresponding to the largest eigenvalue. Right? So this follows, hopefully you all, when you did eigenvectors, did this, but this follows from also the Rayleigh-Ritz theorem, which says that if you have a quadratic form like that involving a matrix, then the W that maximizes that quadratic form is the principal eigenvector of that matrix. Okay? So a very simple solution to get at your principal competence is just form your sample covariance matrix and look at the top k, if you want a k-dimensional projection, top k eigenvectors. All right. So I think we are over time. We'll end here, and then we can just discuss this algorithm and an alternate way to solve it next time.